Okay, pardon that interruption. I had looked over at my notes where I had previously worked this out, and I didn't realize at first I had just done a different sequence of row operations. So since the numbers were looking a bit different, I thought I'd made an error somewhere and wanted to stop and double check. But everything's fine. In any event, so we're taking row 1 and subtracting row 2 from it twice. So row 2 won't change. As you can see, it's just 0, 1, negative 3. And row 1, if you subtract row 2 twice, this 2 is going to disappear because of that 1. This 3 is going to turn into a positive 5 because you're subtracting negative 1 twice. And then this 5, when you subtract negative 3 twice, that's like adding 6, so you're going to get 11. So that's what the first row becomes. Now if we're adding the second row to the third row twice, so what we're going to have here is 0, 0, and then what will happen here, if I add negative 1 twice to positive 1, I'll get negative 1, and if I add negative 3 to positive 4 twice, I'll get negative 2. Okay, so now we're almost done. I can take row 3 and replace it with negative 1, row 3, and it'll turn this into a positive 1, and everything else won't change. So row 1 and row 2 will stay exactly the same, and then row 3 will turn into 0, 0, 1, positive 2. And then now we'll just finish this off. So take row 1 and replace it with row 1 minus 5 row 3. That will subtract this 1 from that 5 times, and that'll clear out this positive 5. And then to get rid of the negative 1 in this entry, we'll take row 2 and we'll just add row 3. And what that's going to give us is 1, 0, 0, and really, what happened here? Oh, yeah, and so if we subtract 1 from 5 times, we'll get 0, and if you subtract 2 5 times from 11, you're getting 11 minus 10, which is 1. And then when you add row 3 to row 2, you're going to get 0, 1, 0, negative 1, and then row 3 won't change. So finally, we've got the solution, and this tells us that therefore C1 is equal to 1, C2 is equal to negative 1, and C3 is equal to 2. But we don't want to stop here, because that's just that's the solution to, I'm going to pull this other page back, that's the solution to this system of equations over here. But remember, the whole point of this system was that it was set up so that we could figure out what C1 and C2 and C3 would have to be so that we could get our coordinate vector. Because remember, the definition of the coordinate vector is it's those coefficients. So that's why we just need to write one more thing down in order to summarize our answer, and we can say therefore the coordinate vector for V, that was the name for the vector we were given, relative to the basis B is going to be 1, negative 1, 2. So that is our answer. This is what we really wanted, and this is what we were asked for. So that's the solution to that example. Now for part B, this one is asked backwards, and the good news is that actually makes the question easier. It's much easier to recover the vector if you're given its coordinates relative to a certain basis. So I just want to remind you what the question was. So we were asked to find the vector W in R3, which has a coordinate vector given by negative 1, 3, and 2. So these are the coefficients we're going to use to build the vector W from the vectors in the basis B. So since, let's write it out like this, since the coordinate vector of W relative to B is equal to negative 1, 3, 2, it follows that we can just write the vector W as, well, just take this vector, or this scalar negative 1, and multiply it by the first vector in your basis. Sorry to keep flipping around, but the first vector in the basis is 1, 2, 1. So we're just going to have negative 1, 2, 1. Really, it's negative 1 times the vector 1, 2, 1. That's the same as just writing a negative sign in front. Then we're going to go plus 3, because that's our second coordinate. We're going to go plus 3 times the second vector in our basis, which is 2, 9, 0. So plus 3 times the vector 2, 9, 0. And then lastly, plus 2 times 3, 3, 4, because 3, 3, 4 is the last vector in our basis. So that's your first step to finding the vector W, and the rest is just to work it out. So let's multiply the scalars in. So I'll have negative 1, negative 2, negative 1. If I put that negative into the vector, then if I multiply the 3 in, I'll have 6, 27, and 0. And then if I multiply the 2 in, I'll have 6, 6, and 8. So let's just add these together now. So if I add all the first coordinates, I'll have -1, 6. Add those together, you get +5. Plus that 6 is 11. And then for the second coordinate, -2 times 27, or pardon me, -2 plus 27 is 25. And then if you add that 6, you're going to get 31. And then the last coordinate will be -1 plus 0 plus 8, which is 7. So that's your vector W. So therefore, if you want to summarize it in one line, you can see therefore W is 11, 31, 7. So that's the actual vector. Don't get confused here. The coordinate vector relative to the basis B is given by -1, 3, 2. That does not mean that the vector W is -1, 3, 2. The vector W is actually 11, 31, and 7. This coordinate vector that we wrote up here that we were given, that's the blueprint that tells you how to build the vector W from the basis vectors in B. So it's easy to get confused by that, but give yourself some time to work with it. When you work on the exercises, make a point of actually, when you write down a coordinate vector, make sure you write down that subscript to remind yourself that you're talking about a coordinate vector with respect to or relative to a very particular basis. Okay, so that's the end of section 4.4. Another big application of a basis is it's going to allow us to introduce the idea of a dimension of a subspace, which is what section 4.5 is about. So we'll talk about that in the next section of videos.